Calm before the storm. Nice and quiet. All right, we finished example 9. So just to summarize, we've already talked about smoothly connected. But before there's this box. And this is what I guess you can call the non-intuitive definition of differentiability at a point. Or the actual definition of what it means to be differentiable at a point. Quantifiable. It says a function f is differentiable at x equals c if and only if. That means bidirectional. So not necessarily just for emphasis, right? If and only if this happens. This is the limit as x goes to c from the left and the limit as x goes to c from the right, both equal L. But what are we taking the limit of in both cases? We're not taking the limit of f of x because that just looks at the y values. Not the derivative, not Dairy Queen, difference quotient. Yeah. If we look at the difference quotients, and notice it's the alternate form, right? It's the alternate form. So basically, if the two alternate form difference quotients, the slope of the secant lines from either side, essentially, if they start merging towards the same slope from either side, then we say the function is differentiable there. And the reason this takes continuity into account, which remember is a necessary pre-existing requirement, is they both use f of c. So from the left we're using the y value, and from the right we're using the same y value, even though the f of x piece could be different depending if we're coming in from the left or right. It has continuity built into it, okay? And if those are true, then we can say that f prime of c exists, all right, and is L. So let's look at example 10. It says, use the definition of differentiability at a point to determine whether the following function is differentiable at x equals 1. Now we actually have truly a piecewise function. And rather than check it the way that we previously did, where we look for the y values separately and the slopes separately, we're going to use the alternate form at least one time, just so we know how it works. Notice to the left and right of 1, it's defined by two different functions. But what is f of 1? Let's find that first. You plug it in there and you get -2, okay? Because that's where the equal sign is. So we have to use that for both pieces. So here we go. Let's do the left side first. The limit as x approaches +1 from the left, and it's the difference quotient. So f of x minus f of 1 all over x minus 1. That's just kind of setting it up generically. We're not looking at the limit of the y values. We're looking at the limit of the difference quotient. Now, what makes this particular to the left-sided limit of 1? Which f of x piece are we using as we come in on the left-hand side, the top or the bottom? The top, right? So less than 1, we're coming in riding the line of -3x plus 1. So that's what f of x is to the left of 1. So we're going to have to use -3x plus 1 right there for f of x. Minus f of 1. What's f of 1? Well, we already calculated it to be what? -2. So I'll put that in parentheses. All over x minus 1. Now, if I simplify that before I dare try plugging in, I get what? -3x plus 3 all over x minus 1. And if you try direct substitution, you get 0 over 0, which means we've set it up correctly. And we know then how to get around it. We factor out a, what from the top? A -3, good. And we're left with x minus 1 all over x minus 1. And they divide out and we get -3. There's nothing to plug into. Now, did we know that before we went through all that work? Or should we have? Yes, why? Good. Good. Coming in from the left, it's the line that has a constant slope, mx plus b, of -3. So it's -3 anywhere and everywhere. But notice, using the alternate form, we just kind of confirmed it. We confirmed Algebra 1. Way to go, us. All right? Now, going out on the right-hand side, it is a parabola. And parabola slopes vary. So we need to make sure, if it is differentiable, that not only is it meeting up at 1, but it's turning from a line to a parabola without any noticeable jag or edge. So from the other side, we got the limit as x goes to 1 from the right-hand side, and it's still f of x minus f of 1 over x minus 1. What's different, though, is the f of x we're using coming in from the right-hand side. Because notice it says when x is greater than 1, we're using the variable function f of x to be x squared minus 2x minus 1. Minus, what is f of 1 still and always? It's still negative 2. And so that's how it takes the continuity aspect into account. And then all over x minus 1. So if I simplify that, I get the limit as x goes to 1 from the right of x squared minus 2x. That's going to be 2 minus 1 is plus 1 all over x minus 1. And what do we get when we use direct substitution? We get 0 over 0. You can verify it, which means that we can factor the top as x minus 1 times something, namely x minus 1 times x minus 1, I believe, binomial squared, all over x minus 1. So I wrote it side by side so I can go, and then I plug into what's left, and I get 1 minus 1 is 0. And now all I got to do is compare those two numbers. It's kind of like the test for continuity, but we're only testing 2 things instead of 3 things. We're not really looking at the bridge. We're just looking at what the slopes are approaching. So we're only looking at the roads. So if either one of these 2 fails to exist, or they don't equal each other, if they both exist, it's not differentiable. So does negative 3 equal 0? No. No, it does not. No, it does not. Right, you just cite the reason. So f is not differentiable at x equals 1 since, and then you can recall those numbers, negative 3 does not equal 0. Now, if I let you do it another way, you might be able to answer it a different way than using the alternate form, but the alternate form does work. Let's go ahead and see what you would do first if I told you to do it in the future. Remember, being continuous is a necessary precondition, so check for that first. That's real easy to check for, right? Because now we're just taking the limit not of the difference quotients, but of the y values themselves. What's the limit from the left of 1? Negative 2, which is also the function value, and the limit from the right of 1 is negative, it is negative 2, right? So is the function continuous at negative 2? Yes, so the graph is connected. Now later on, you're going to know how to take the derivative of the bottom piece very, very easily to get your piecewise f prime. I don't know how you did that, but anyway, later on you're going to be able to quickly and easily find a piecewise f prime, and then you'll be able to take the limit of f prime from the left and right. And if those numbers are the same, then it would be differentiable, but you'd find out here that they're not. So this function is continuous, but not differentiable. So let's kind of think about what's happening here. It's changing from a line with a negative slope to a parabola that opens up, but it's not a smooth connection. This would be like a smooth connection, right? If I drew it like this, would you be able to tell exactly where it changes from a line coming in on the left to a parabola going out on the right? Right now, you could come up here and pinpoint exactly. Well, I had to draw it twice, but make sure, maybe I don't do that. Maybe I draw it as a line coming in, and then it turns to a parabola. Now, Peter, can you come up here and point exactly on the graph where it changes from line to parabola? No, you cannot. Good. Because this would be a differentiable function. Yes? But if I drew it like this, and then I kind of went like that, now, Peter, could you come up and point exactly where it changes from line to parabola? Yeah, I know you could. I have more faith in your abilities than you. Yes, it would be right there. That would be a cusp. Right. This would actually have a negative slope from the left and still a negative slope from the right, but they're not the same negative number, right? It's steeper on one side than it is on the other. So that's what a cusp is going to become to be known as. A place where the 2 slopes on either side are not the same. You get kind of like a little jagged barb or point there. All right, sweet. Now, there's another mathematical synonym for differentiability, and it's called locally linear. But I'm not going to record this because it's already recorded. So I'm going to stop the recording here and then talk to you about locally linear.